All right, Engineering and Compiler, Chapter 2 Summary on Scanners. Remember, scanners are part of the front end, so this is what a compiler looks like. The front end is the first part of the 3 steps in the compiler, and the scanner is the first part of the front end. All right, so the vocabulary for this, we have a lexeme. This is the string of characters from the source code. We have a token, the category or part of speech that the lexeme belongs to, and the pattern, and that's the rule that describes all valid lexeme for a specific token. So this is what it would look like if we have the string int score equals 100, right? That would be made up of int, the pattern, or the lexeme would be the int characters coming in as a string. The pattern would be the strings or the letters int in that order, and the token would be type int, right? And then for score, it's a little different because the score is the variable for it. So the pattern for that would be any letter followed by any number or letter. So a letter followed by alphanumeric characters. And that would be an identifier. So that'd be an ID. And yeah, this is just a good example. So how do we describe these patterns? These patterns, they're pretty clear. A letter followed by any letter or numbers, right? But how do you describe that? Pretty easy with regular expressions. Regular expressions are, I learned about them in my Linux class, but they're made up of concatenation, which is just combining like A followed by B, like that, A, B. Alteration, which would be union, A or B, which is just a vertical line. Closure, which is also called the Clenny star. And this is just A star, which is 0 or more of the A. And then A plus is 1 or more A's. And we also have brackets, which is a set of all possible character matches within the brackets, if that makes sense. And the order of precedence is obviously brackets first, and then closure, concatenation, and then alteration. So an example of that would be this. You might not be able to immediately tell what this stands for, but this would be the pattern for the word or the variable score, right? So we have any letter, so A through Z, lowercase, or A through Z uppercase, right? So any letter followed by any lowercase or uppercase letter or number, and 0 or an infinite amount of them, right? So that's any letter followed by alphanumeric characters. So that's what this pattern stands for. So this would be the pattern for score. So pretty simple. But how would we execute the pattern? So we know the pattern exists. We know how to write the pattern. How do we execute it? That's where you get finite automaton. Best described as a very limited Turing machine. So if you're not familiar with what a Turing machine is a theoretical best computer. And that would be a computer with an infinite tape or infinite amount of RAM that it can move around on one square at a time, left or right? And every square on the tape or piece of the tape can be written or read, right? So a finite automaton is a limited version of that. It's a fixed size tape, and instead of being RAM, it's more of an input stream that the head can only move right on. So it's more like an input stream, right? It's just a string of characters that are being read, right? The head can also only read from the tape, it cannot write. And there are also a limited number of possible states, right? So for our example right here, int score equals 100, Well, first, this is what, if you took discrete mathematics, you're probably familiar with finite automatons. This is what they might look like. They also look like this with multiple states. And if we were going to go take the word int and make a finite automaton for that, right, you'd start at S0. If you get the letter I, you move to state 1, and now you're in state 1. And if you get the letter N, you move to state 2. And if you don't get the next letter, right, you'd go to SE, which is S air, like air state. Yeah, so now we know what finite automatons are. There's two different types of finite automatons. We have non-deterministic finite automatons and deterministic finite automatons. Non-deterministic finite automatons are easier to make, right? They're easier to construct, and they also allow for multiple transitions out of one state on the same input character, right? I'll show an example very soon. They also allow empty string transitions, so it can move to a different state without consuming any input. And here's an example, right? Non-deterministic finite automaton. Here's my laser pointer. So on state 0, you receive I, and it moves to both state 1 and 4, right? So now it would be in both of those states at the same time. That's what makes it non-deterministic, because at that point, after you entered an I into the system, you'd be in two states at once, and then you would determine which one you would actually move to after you receive the next letter, right? So if you receive an M, it would just become state 5. And the thing about non-deterministic finite automatons is you can always convert them into deterministic finite automatons, right? And those are better because for every state and input character, there's only one transition. So that's our example above. This is a deterministic finite automaton. And like it says here, you can always convert a non-deterministic finite automaton to a deterministic through subset construction. And that, like, an easy example is this, right? You have I that splits up into two different states. Well, what you can do is you can just collapse those states into one. And if you get I, go to state 1, and then based off state 1, split, right? So that's a pretty good rule, easy rule of thumb, right? So there's two different types. Well, now we know regular expressions are made up the patterns, right? And non-deterministic finite automatons are easy to make based off regular expressions, and all non-deterministic finite automatons can be turned into deterministic finite automatons. So what we want to do is we want to turn regular expressions into deterministic finite automatons. So we do that with Thompson's construction. That's from regular expression to non-deterministic finite automaton. That's by turning just by turning every part of the regular expression into a non-deterministic finite automaton. Then you turn the non-deterministic into a deterministic, as we've shown here, right? And we do that through subset construction. And then we use Hopcroft's algorithm, which minimizes the deterministic finite automaton, right? And it provably minimizes the deterministic finite automaton to its smallest state, right? So an example of that is this. We have the deterministic finite automaton for the words bot and not, right? So we have B and N, they split to different states. And then we have the letters O and T that are the same for both of the words. So instead of having two separate paths like here, we can simply collapse them to separate and then go back together. So now this is the provably minimum deterministic finite automaton. So that's what Hopcroft's algorithm does. So now we have the smallest implementation of a deterministic finite automaton. Now what we have to do is implement it, right? That's great. There's two ways of implementing it. We have the table-driven approach. This is the simpler approach, kind of, and it can be easily created with a script that just loops through, checking all the different paths essentially, and it creates a large 2D array of state transitions. And this can get very large and it might not fit in the CPU, which causes cache misses and which will slow down the script considerably compared to a direct coded example. For example, ASCII, right, has 256 characters. Multiply that by the number of states, it's going to be a lot. It's going to be a huge array, right? So here's an example of that. We have Hopcroft's algorithm, right? This is the minimum deterministic finite automaton, and converting this into a table-driven approach, we would have the following, right? The states along the top, S0, S1, that's each one of the nodes, and then the inputs on the side, where we have B, N, O, and T, right? Those are our 4 inputs. And if we're on S0, right, and we get a B, we go to S1, right? And every SE is an error state, right? So this is pretty intuitive, but imagine the inputs being 256 characters and probably hundreds of states. That's going to get very large. So the other approach we have is direct coded. This is where you transition between states using go-to statements, right? So it's hand coded in this example, right? So you transition between states using go-to statements or infinite loops with switch cases, right? So it's faster and smaller because all the code is explicit. However, much harder to maintain and much harder to make and debug. It usually has to be done by hand though, because just because, because it becomes unreadable spaghetti code. And it's better because it's way faster than the table-driven approach. So what are some of the problems we have with this scanner? Well, we have input buffering problems. So it's very slow to get one character at a time from the disk. So simply take a page or another, like whatever the page is for your machine, like just take a large number, like 2048 bits, or some other large number, and just take one page of the characters at a time. The book recommends a 2-page buffering system. This is where one page is being read while the other is being loaded, and then they switch, and the other page is being read and the other page is being loaded. So that's like this with page 1 and page 2. So it would load page 1, the script would start running on page 1, and while it's still running, it would be loading page 2. And then it would continue and then switch. Another problem is handling keywords. So we have 2 options for this, right? Option 2 is obviously better, but option 1 is you encode IF and then space as a path in your deterministic finite automaton, right? But the problem with this, or making like the path IF as an identifier, because remember, it parses out the word, and then it also gives an identifier of what the type is, right? So if we go to the very top, we have the token, right? This is the identifier. So we have the pattern, which finds the word int, but then you also have to call it of type int, right? You send both of them to the next step of the front end, right? So here we are. So you can encode it directly, right, with IF space, but this is really bad because it makes the deterministic finite automaton massive, right? The second option is you treat everything like an ID and or a variable. And once the word is finished, once you reach that space or whatever that ending piece is, you check a hash table and see if the thing you parsed out is within the hash table. And if it is, you change the identifier. So if you find the word if, you'd be like, oh, that's a variable. And then you check the hash table and be like, oh, it's not a variable, right? So that's very good for minimizing the size of the program, right? Another thing that's a problem is look ahead. Sometimes you want to look ahead to see if, like, for example, an equal to is just an equal to, or if it's like an equal to or greater than. You want to know if the equal is an assignment or a comparison. You know what I mean? So sometimes looking ahead can be useful. This is useful when there's like the two input buffer pages. You can only do it with the two input buffer pages. So if you're reading in one character at a time, it makes it impossible to read one character ahead, right? But when you're buffering in like 2000 bits, it's very easy to read a couple of characters ahead if you want to, right? And then, so like, here's an example. It's like helpful for inputs like while true, right? So when it sees the first open parentheses, right, it'll know that it's a while loop and that it's not an identifier, right?